Okay, so this is question 4. It's a fundamentals in chemistry question. It's from module 1. And so they're asking us to describe how the bonds are formed in each of the solids, potassium chloride and iodine, right? And this is worth 4 marks. So let's be guided by that in the length of our answer that we're going to give, right? So potassium chloride, let's just kind of write that down from a formula standpoint. The KCl, so that's potassium chloride, it's KCl, right? And right now we can see that it's an ionic compound, right? So ionic compound. And then, of course, we know that we have iodine. That's a molecule. It's a diatomic molecule. And of course, it exists as a solid at room temperature, right? So that's a halogen that's at the bottom of the group. It exists as a solid. It's a diatomic molecule. What else can we say about iodine off the cuff? We know that there are going to be covalent bonds predominating throughout, right? So those are covalently bonded. Those atoms are covalently bonded to each other. So there are covalent bonds there. And of course, we know that they're solids, right? Okay, so let's talk a little bit more about solid KCl now. It's an ionic compound, as we show here. It's comprised of these potassium ions and these chloride ions, right? And so essentially what we have is close packing of ions. So we can kind of typically depict that as alternating positive and negative charges that are closely packed to one another, right? So that's what we have in ionic compounds. Close packing, right? So we have close packing of ions, right? We see that. We have close packing of ions. And then there are strong bonds that are formed between those oppositely charged ions, right? Strong bonds formed between oppositely charged ions. Okay, so now we're talking about solid I2, right? We mentioned earlier that there are covalent bonds that comprise those. And so we can look at this on 2 levels, right? For iodine, we have our 2 iodine atoms that are bonded to form an I2 molecule, right? And these ones, they're covalent bonds between those 2 atoms. So on that level, right, they're on a single molecule level, there are covalent bonds between, right, those 2 atoms, between 2 iodine atoms that come together to form that one molecule, okay? But then now there also exists some van der Waals forces, right, between each iodine molecule, right? So we have another iodine molecule over here that's also comprised of 2 atoms, and between that and another one, and then we can imagine that there's another one as well, right? These bonds here are van der Waals forces. So we kind of say in iodine, they're like mixed bonds, right? On some level, we have van der Waals, which I'm writing as just VDW, van der Waals forces that connect the molecules to each other. Van der Waals forces there. But of course, we mentioned that within the iodine molecule itself, there are covalent bonds, right? That hold them together. So these ones would be covalent, and then van der Waals that hold the molecules together, okay? So that's a mixed bonding system that we have going on here in iodine. Yeah, so let's just like summarize that in words here. We have weak intermolecular bonds between I2 molecules, right? So that's one I2 with another I2. So we have weak intermolecular bonds between I2 molecules. And that those weak intermolecular bonds that holds them together in a 3D lattice, right? In a 3D lattice. Okay? So a simple molecular 3D lattice is what we have there. So let me just add up here. It's a simple molecular structure. Simple molecular lattice, right? So that's what we're working with there. And so with that, we should be good for our 4 marks, okay? All right, so here we go now. Clear this. Okay, so now we're just filling out this table 3 by comparing the physical properties of potassium chloride and iodine, right? So properties that we have are melting / boiling point, we have electrolytic conductivity, and we have solubility in water. So of course we know that these properties, these physical properties here are connected, are very intimately linked, right, to the structure and bonding of these particular compounds. So we just discussed structure and bonding, so we should be able to deduce how these properties would fare in each of these compounds, okay? So let's look at KCl first. We see that KCl has a high melting or boiling point, which we can see that it would be that would be the case because it's an ionic compound. And so because there are ions in it that are mobile and free to move about, then of course it would have high electrolytic conductivity as well, right? Ionic compounds are generally good electrolytic conductors, so we would say that this is high. And as it relates to iodine now, this iodine molecule, it has a low melting point because those kinds of simple molecular compounds are very comparatively weaker bonds when compared to ionic compounds. So it makes sense that this would be low. And then as it relates to electrolytic conductivity, right, we have a solid state iodine molecule. And there are no free ions, there are no charge carriers in it, right? So the conductivity would be low, if at all existent, right, in iodine. And when we look at solubility now, by the same token of there being ionic bonds in KCl, we know that it would be soluble in water, right? So this would be soluble in water. And we know that the iodine solid is insoluble, right? That's a solid compound that's insoluble in water, right? And that's by virtue of its bonding as well, right? It's not able to form any interactions with water. Water's hydrogen bonding in it doesn't really work well with these simple molecular compounds like iodine, right? So it would be insoluble. So this is how we'd fill out this table, and we would be able to get our 2 marks in the bag, and we're ready to move on, right? So that was part 2. We're ready to move on to what's next. So I'm just gonna clear this and move down. We're gonna move down to part B, right? So part B is saying that we are supposed to account for each of the following statements, right? The first one is that the boiling point of H2O is higher than that of H2S, right? So they're saying that we should account for that. Why is it that the boiling point of H2O, water, is higher than that of H2S? And really, what this comes down to is the fact that there's hydrogen bonding, right, present in water. So let's just write that down. Hydrogen bonding is present in H2O, but not in H2S. So right off the bat, like that alone changes the game, right? We know that hydrogen bonding forces are very strong, right? Forces of attraction due to, I'm just going to say H bonding, but we know that's hydrogen bonding, are very strong. And so it will be very hard to break apart those water molecules to change from a liquid state to a gaseous state, right? Because that's what boiling is involved in, right? So change from a liquid state to a vapor phase, right? It's gonna be super hard to break those bonds. Whereas in H2S, so in hydrogen sulfide, right? We have no H bonding is present, as sulfur is not as electronegative as oxygen. So there are weaker forces of attraction in H2S than water, and so it will be easier to change its state from liquid to gas or vapor. And so we see a lower boiling point for H2S than water. Okay, so it really just comes down to the fact that water has hydrogen bonding and H2S doesn't, and hydrogen bonding we know is like a master force, right? A master intermolecular force. And so because of that, the boiling point of water will end up being higher, okay? So that's what we would put there for our 3 marks. And so let's clear that. And then we're ready to move down to part I of B, which is saying that we're supposed to explain, right, account for the statement that the molecules of aluminum fluoride in the presence of ammonia forms a white solid of formula NH3ALF3. And they said we should include an appropriate equation in our account, right? So I guess the first thing that we need to do is just kind of draw what aluminum fluoride looks like, and then show how that would change once we bring ammonia into the picture, right? So I'm going to draw what aluminum fluoride looks like. So that's ALF3, right? That's what we would form. That's the formula for that compound. And it would just be Al is bonded to F, F, and then there's another F, right? So let's see here. So what else? Aluminium has a valency of 3+, so Al is 3+, and then we know that fluorine is -1, right? So every fluorine would receive, right, would be bonded with that those 3 aluminium. So that's how well, let me just repeat that. So there are gonna be 3 fluorine molecules, 3 fluorine atoms per aluminium, right? So that's what our formula is, ALF3, and so this is the structure that's gonna be formed pretty much, right? And so when we bring ammonia in the picture now, we know that ammonia has a lone pair on that nitrogen there, right? So what can happen is we can form what we call a dative covalent bond, where this ammonia donates these 2 electrons to the aluminum here, right? So that's a dative covalent bond because it's going to give all of its electrons to the aluminum. So we have a dative covalent bond. And so when that happens, right, and the ammonia gives its 2 electrons to aluminum, then what's going to happen is we're going to end up having this structure here where we have H, N, A. So this is just your ammonia that's then attached to the Al, right, which had a F here, a F here, and a F here, right? And so what we see then is that there's a white solid, and this is our white solid that we see, right? So this compound here is our white solid. So that's how that would be formed. Okay, so white solid of NH3, AlF3, right? So we started out with this ionic bonding structure here with between Al and the 3 F atoms. And then when ammonia comes into the picture now, what it can do is it can donate those 2 electrons that it has to then form what we call a dative covalent bond with the aluminum. And so we end up getting this more complex structure, which is that white solid that we see. And that has the formula NH3AlF3, okay? So this is what we would put down for 3 marks and we are good. So I'm just gonna clear this and move down to see what else there is. Okay, so for part C, they're asking us to explain the difference between the shapes of ammonia and the ammonium ion, right? So first of all, we're gonna have to draw our covalent bonding in these different molecules, right? So then we can deduce the shape using the VSEPR theory. So let's just write down the steps here. So first, we're gonna draw the covalent bonding present in each of these molecules. And then after we do that now, we're gonna use VSEPR theory to deduce shape and explain difference. So that's how we're going to approach this one. Okay, that's what we're going to do here. So let's draw the covalent bonding that's present in ammonia. So let's start there. So in ammonia, it would be what? We have a central atom of nitrogen. So this is our nitrogen. And then we have 3 hydrogens. So 1, 2, 3. Right? We know that nitrogen is what? 7, so it's 2, 5. So there are 5 valence electrons. And we know that so these are the valence electrons, right? And then for hydrogen, there's just 1, right? So what's gonna happen now is that the nitrogen needs 3 to get to 8, right? So we're gonna have, let's use different colors. So blue shows the electrons that are from the nitrogen. So that's 1. And then let's have green show the ones from hydrogen, right? So this is hydrogen. This is a hydrogen and this is a hydrogen. They only have 1 electrons, right? So 1 electron. So that, and then that is what we're gonna get. And then of course, 1 from nitrogen and then the other from the hydrogen. All right, so that's what we have. So let's see what we're working with here now. So we have 5. Remember that nitrogen has 5 in total. 3 are involved in bonding. So there's a lone pair here, right? So X, what did I put X in? Blue for nitrogen. So nitrogen's electrons are in blue. So that's X here and an X here that aren't involved in bonding. And the ones that aren't involved in bonding, we say that's a lone pair, right? So that's a lone pair there. So in the end, at the end of the day, for this ammonium compound, we have one lone pair and we have 1, 2, 3 bonded pairs, right? 3 bonded pairs, right? So let's do the same. Let's draw the structure for the ammonium ion. So for the ammonium ion, we have 4 hydrogens and 1 nitrogen. So that would be, so let's draw a central nitrogen and then let's draw 4 H's. So that's 1, 2, 3, 4, right? And again, nitrogen has 5 valence electrons, so we have to make sure that we account for that. So let's write down, or let's draw all our nitrogen electrons. So that would be 1 here, 1 here, 1 here, and 1 here. And then let's draw our hydrogen ones in green. So this is hydrogen. These are all hydrogens. Hydrogen, hydrogen. And so this one, these circle, open green circles are from the hydrogen, the electrons from the hydrogen, right? So we see that in this particular case, we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons all around the nitrogen. So there are 4, and they're all involved in bonding. So there are 4 bonded pairs in that case. And of course, 1, 2, 3, 4, the 5th one was what the ion lost. That's why we have this plus charge on it. So like if I were to like just complete it, we say that this is the ion, so it's plus, there's a plus on it, right? And that's what we account for there only being 4 electrons from the ammonia here, from the nitrogen, sorry, here, right? So there are 4 bonding pairs in all, 1, 2, 3, 4. And in this case, there are 1, 2, 3 bonded pairs and then 1 lone pair, right? When we have 4 bonded pairs, so bonding pair repulsion, according to the VSEPR theory, is the least out of all of them. And so what's gonna happen is if we have 4 bonding pair, the bonded pairs are gonna repel each other in such a way that we're gonna end up with a tetrahedral structure. So for ammonium ion, we're gonna see a tetrahedral structure because there are 4 bonded pairs, and the bond angle is gonna be 109.5 degrees, right? That's what the bond angles are in tetrahedral structure. And then for the ammonia now, we have 1 lone pair and 3 bonded pairs. So the lone pair, bonded pair repulsion is greater than it would be if it's just a tetrahedral structure where there are only 4 bonded pairs, right? So we're gonna get a different shape for this molecule. And that shape is gonna be what we call trigonal pyramidal. Pyramidal. And what's the bond angle in that case? The bond angle of a trigonal pyramidal structure is around 107, right? So that's the bond angle that we're gonna see for a trigonal pyramidal structure where we have 3 bonded pairs and 1 lone pair, right? So that's what we're gonna have for our bond angle. So our bond angle for trigonal pyramidal is gonna be 107 degrees, right? So that's really how we explain the difference in the shapes that we see, right? In the one case where it's ammonia, there's 1 lone pair and 3 bonded pairs. And from VSEPR theory, let's just kind of recap the level of repulsion, right? So the lone pairs are gonna repel each other more than a lone pair and a bonded pair. And then that's gonna repel more than a bonding pair next to a bonded pair, right? So in this case, because this is like in the intermediate here, there's going to be a reasonable amount of repulsion between the lone pair and the bonded pairs that are around it, such that we end up with a trigonal pyramidal structure of bond angle 107 degrees. And then in this case, all we have are bond pair, bond pair, bond pair, bond pair, and they're repelling each other, but to a lesser extent than it would be over here. And so we say that bond angle is slightly higher, which is 109.5, and so we get a tetrahedral structure out of that. Okay, guys? All right, so that is that for part C. So let me clear this real quick.